In this lesson, we'll delve into the mathematics of Fourier transforms in two dimensions. First, let's talk about an image as a signal. We can think of an image as a two-dimensional signal where each pixel takes the place of a sample in a 1D signal. Remember, the 1D signal was based in the time domain, but there was no specific time coordinate. The sequence of samples implicitly defined the time coordinate. But in a 2D image, we actually have explicit spatial coordinates. The 2D image is in the spatial domain, and we have x and y, or m and n, as the spatial coordinates. Each pixel or each sample in the image has the value fmn, which represents the pixel intensity. Of course, pixels are discrete, so only the discrete Fourier transform applies to images. And as you might imagine, the outcome of applying the Fourier transform to the image is that it maps the image from the spatial domain to the frequency domain. But whereas signals only have one frequency, images have two frequencies, one along the x dimension and the other along the y-axis. And we'll talk in a later lesson about what it actually means for an image to have a frequency, or actually a pair of frequencies. So the formulas for 1 and 2D discrete Fourier transforms are extremely similar, except that instead of summing over one dimension, which is time, we have to sum over two dimensions, which are the x and y dimensions. We'll talk more about this formula later, but basically in 1D Fourier transform, we had n time samples, each of which had a value of x sub n, whereas in the 2D we have m times n pixels, each of which has a pixel intensity or a value of f of mn. Here we summed only in one dimension, which was time. Here we're summing over two dimensions, which are the two spatial coordinates. And finally, the time complexity of this was n squared, whereas the time complexity of this ends up being m squared times n squared. So let's look at this formula in more detail. Again, we have two sums because we're summing over all rows and all columns to retrieve each pixel's value and multiply the pixel value by this exponential function, just like we did in the Fourier, in the 1D Fourier transform when we multiplied the sample value by an exponential function. And we end up with this. Each Fourier coefficient has two coordinates. Just like an image is two-dimensional, the Fourier transform of an image is also two-dimensional. So each Fourier coefficient has a u coordinate and a v coordinate, which actually correspond to the two image frequencies. Now, because before we just had one index k, and now we have two indexes u and v, we can't just have one omega to simplify this formula. So if we want to streamline this formula, we need to define two omegas, one across all the rows, wm, and one for all the columns, wn. And you can see that their structure is extremely similar to the omega in one dimension. So applying this simplification, we end up with this formula for the 2D discrete Fourier transform. And as you can see, the formula for the inverse Fourier transform is extremely similar, except that here we have negative exponents, and then we have to normalize the sum by dividing by the number of pixels, just like we did in the 1D Fourier transform. Here's a comparison of the formulas for the forward and inverse transforms between 1 and 2 dimensions. Just a word about what we end up with. First of all, after applying a Fourier transform in one dimension, we come up with a spectrum that we usually call a frequency spectrum. When we apply it in two dimensions, for some reason we call it the magnitude spectrum, but they really are plotting the same thing. In both cases, we're plotting the magnitude against the frequency. Except that here we have two frequencies, u and v, so in order to plot the magnitude, we represent that as the brightness of each point on this graph. Also, remember I told you before that the Fourier transform returns both positive and negative frequencies. Previously, I had only shown you the positive frequencies, but this is the actual frequency spectrum of our guitar sound signal. There's a 0 in the center, and they are symmetric across the positive and negative frequencies. The same thing is true of the magnitude spectrum. We have a negative u frequencies and positive u frequencies, negative v and positive v frequencies. Actually, and negative is here and positive is here for v. And so we end up with this very symmetric a plot that's symmetric both across the u and v axes. So what's next? Next, we're going to use these formulas to implement our own 2D Fourier and inverse Fourier transforms from scratch. If we want to streamline this formula, we need to define two separate omegas. One is omega sub m, which applies to the rows or the y-coordinate of the image, and the other one is omega sub n, which applies to the columns of the image, and they both have extremely similar formulas to the omega we used in one dimension. So when we apply this simplification, we end up with this as the equation for the 2D discrete Fourier transform. And just like before, the inverse discrete Fourier transform, it has an extremely similar structure, except that here the exponents have negative coefficients, and then we normalize the sum by dividing by the number of pixels. And this is a comparison of 1D and 2D forward and inverse transforms. So what's next? Now we're going to use these formulas to actually implement our own 2D Fourier and inverse Fourier transforms from scratch in the next coding assignment.